Indiana University East, power generated in a wind turbine. Dr. UK Law. In this video, what I'm going to try and do is to explain the physics behind how a wind turbine works and try and get a sense of how much power can be realistically generated from one, given the local conditions. So this is the physical problem. We've got a wind comes in with a certain kinetic energy. And we are basically going to slow down, or ideally completely stop the wind. Okay? Stop all this incoming wind. We have a wind turbine. And use that kinetic energy to drive this, which then this rotates and it drives a dynamo, which gives us electrical energy. Okay, so for an ideal turbine, we're converting all this kinetic energy here, so there's basically no kinetic energy here. And so the energy produced is equal to the kinetic energy of air that passed through. Okay, so times the efficiency of the turbine. This inefficiency comes both from the dynamo setup, which is not the major issue, but rather you can't actually stop block the wind, and therefore that is a source of inefficiency, if you will. Kinetic energy, as you may recall, can be modeled by the equation energy is equal to half mv squared. So the question then becomes, what is the mass? The mass is actually of the air. So if we're looking at the energy produced in time t, the mass is the mass of air that would have passed through the cross-sectional area A here. A being the cross-sectional area of the turbine. And if there was no turbine, some mass of air would have passed through. And this, if you go through the mathematics, we can show that the power generated is equal to half times rho times A times V cubed. Rho here is the density of the air, and this is in kilograms per cubic meter, and typically it's about 1.3 kilograms per cubic meter. A is the area swept by the turbine. So if I have these turbines like this with a radius r in meters, then this area is going to be pi r squared. And finally, the speed here, v, okay, is going to be the wind speed in meters per second. This will give us the power generated in watts. But the wind turbine doesn't actually block off all the wind. Otherwise we've got a problem. We've got all these wind turbines. Boom! 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 It'll get knocked off anytime soon. These wind turbines are designed to be fairly efficient. They work at a particular wind speed. It's about 50% efficient if it's working at the right wind speed. It turns out that this is actually very close to the theoretical maximum. It's as described in your book. So we will use this number. So the power is equal to 1/2 density area times the speed cubed times the efficiency. Now, let's estimate this. Half, we said that this is 1.3 kilograms per cubic meter times the area of a circle is pi r squared. So it's pi times, now this is the diameter, so the radius is half of the diameter, which is equal to 57 meters, times the speed, which is, we set in Richmond, is about 7 meters per second, and we will cube this times 0.5 for the efficiency, which is about 1 times 10 to the 6 watts, which is 1100 kilowatts. So the annual energy output is equal, let's say 1000, 160, is 1000 kilowatt hours. Okay, so that's per hour. So there are 24 hours in a day, and then there are 365.25 days per year. So that's about 10 to the 7 kilowatt hours per year. And so that generates enough power if you go through and look at the fact that there's 9.1 times, we use 9.1 times 10 to the 4 kilowatt hours per year per head. It comes out to be about 105. We can generate, using one wind turbine in Richmond, enough electricity, enough energy for 105 people in the US.